396 minus 1.1 times your Ohana status plus 0.0579 times your BMI level. So now the coefficient of Ohana is 1.01. We take e to that number, we see that the adjusted odds ratio, meaning controlling for body mass index, people who got the intervention, their odds of dying was 0.33 compared to those who didn't get the intervention. This is if the model is correct in its assumption of controlling for body mass index by including it as a single term, assuming a linear relationship between body mass index and your log odds of dying, then this model says controlling for body mass index, people who in the intervention group had an odds of dying which was 0.33 of that of the control group. And we can compare that to the previous model we fit, which didn't control for body mass index. Let me just click that. Remember, it was 0.36. So it's changed from 0.36 down to 0.33 by controlling for the body mass index. So it's changed very little, suggesting that body mass index, if it is a confounder, is not a very strong confounder. Controlling for it or not controlling for it gives us roughly the same answer. People in the intervention group have roughly about a third of the odds of dying compared to people not in the intervention group. In other words, that's a strong beneficial effect, a strong protective effect. And it's significant, because if I go back to the model and look at the row called Ohana, there's the log odds ratio minus 1.1 with its standard error. Here's another test, the wall test, with a value of 34.9898. That's different from the tests on the previous page. If I go back to the previous page, notice the chi-square tests for the global null hypothesis were around 50. Now we're looking at a model, a test, whose chi-squared value is about 35 because it's addressing a different hypothesis. It's addressing the hypothesis that we're mainly interested in. It's addressing the existence of that dotted line in that causal diagram. It's saying controlling for body mass index in this model, is there a relationship between the Ohana variable and your mortality outcome? And the null hypothesis is that the true coefficient of Ohana is 0, which means the true odds ratio is 1. And it's saying, controlling for body mass index, this data doesn't support that null hypothesis. It does suggest that there might be a relationship. In other words, it suggests the existence of that dotted line. And the coefficient, minus 1.1, when you turn it into an odds ratio, actually gives you an idea of the strength of that dotted line. It's a strong relationship. People in the intervention group have roughly a third of the odds of dying as people in the control group. But all this depends on the appropriateness of the model and its assumptions. And this model is assuming the best way to control for body mass index is by a single term, which assumes a conditional linear relationship. But there are different ways of controlling for body mass index. So for example, I'm going to go back to my editor. Let's look at the next piece of program. This says, let's fit a model, and that's going to look at the log odds of death based on Ohana and now BMI class. So instead of using BMI, it's going to use the BMI class. Let me go back up to show you what the BMI class is. And the BMI class is a 1, 2, 3, 4 variable. It's equal to 1 if you're underweight, and I don't think there were anybody in this data set who was underweight. Everyone was either normal weight, overweight, or obese. The normal weight people are 2s, the overweight people were 3s, and the obese people were 4. What I'm going to do is now include that as my confounding factor, not the continuous BMI variable, but the categorical variable, BMI class, as I'm scrolling down to where I was before. But now it's going to be a little bit different. I include a class statement here. What a class statement tells me is what comes after the word class, BMI class is the name of the variable that comes after the word class, is a categorical variable. And what I want SAS to do is I want it to create indicator variables to indicate whether an individual is a normal weight person, an obese person, an overweight person. So the way you do that in SAS is two ways. You can by hand create the categorical variables. So if I go back to my program, I could say, and I'll just give you an example. I could say, for example, if BMI class equals 4, then I'm going to create a new variable, an indicator variable. I'll say then BMI, let's see, Fran cannot type very well, BMI class 4. else, I'll say else BMI class 4 equals 0. What this says is anybody who's a BMI class equals 4, anybody who's in the obese category, on this new variable, BMI class 4 is equal to a 1. Everybody else is called a 0. This is an example of an indicator variable. It indicates whether you're in the obese category or not. People in the obese category have a value of 1. People in the non-obese, who are not in the obese category, have a value of 0. Hyper-10, we made a few lines above this, is an example of a indicator variable. It indicates whether you have hypertension or not. People who are equal to 1 are people with hypertension. Otherwise, people with 0 are people without hypertension. The male variable I gave you for the gender, the sex of the individual, is an example of an indicator variable that I created for you. A 1 meant you were in the male sex category. 0 meant you were in the female sex category. So one way is you can create these variables yourself by creating a series of 1, 0 variables, 1 to represent membership in a particular category of the potential categorical variable of interest, 0 otherwise. Or you can have SAS create them for you. And that's what I've done in this program. So I'll go back to where I was, bottom of this. By specifying the command class as part of this proclogistic sequence, it says whatever comes after the word class, whatever variable name comes after it, is an example of a categorical variable. And I want you, SAS, to create these 1, 0 variables for me. Now, it turns out that if you have, in this case, 3 categories, obese, overweight, and normal weight people, you can create 3 different indicator variables, 1 for the obese people, 1 for the normal weight people, 1 for the overweight people. But you only need to include 2 of them in your category, in your model, because by definition, the one that's left out becomes the reference group that everybody else is compared to, as you'll see in a second. So if you want to tell SAS which category you want as your reference, then you do this on that same command, because I put on the same line, in parentheses, param equals ref equals single quote 2, close parentheses. Param equals ref is the command in SAS for it to create indicator variables. Ref equals quotes 2 quote means that's the reference category that I want all the other categories to be compared to. Now remember, BMI class was coded as 2, 3, and 4. Actually 1, 2, 3, and 4, but there are no 1s in this data set. I want to compare the obese people to the normal weight people. And I want to compare the overweight people to the normal weight people. I want to compare everybody to the normal weight people. So I'm going to make the 2s, the normal weight people, my comparison group, and that's what this does. It's probably easiest to show you what happens if I run this program. So what I'm going to do is I'm going to run this new proclogistic. It comes on the bottom of my output screen. I'll go back to the result window. Let's pick up the model information. Looks the same as we had before, 172 deaths, 500 people didn't die. We're still predicting the log odds of dying, but now there's some new information. First thing it gives you is an indication of the variables it created. It created what it calls a design variables. That's another word for indicator variables in this example. It created a variable, if I look down the column, of 1s and 0s. One variable it created was a 1 if you happen to be BMI class equals 3. 0 if you weren't in that category. So 0 if you were obese, or 0 if you're normal weight. It created another variable called 1 if you're obese, 0 if you weren't obese, if you were a 2 or a 3. In other words, this last indicator variable it created, 0s for the normal weights, 0s for the overweights, 1 for the obese people, was the same as the BMI class 4 variable I created a minute ago by hand when I typed it into SAS. This other variable, 0, 1, 0, is an indicator variable for being in the overweight category. It's 1 if you're overweight, 0 if you're not overweight. And what it's going to do is include both of those indicator variables in your model, as I'll show you in a second. Then it tells you something about the fit of the model. The -2 log L for the intercept-only model is 764. It goes down to 720 now when I fit the model with Ohana and indicator variables for body mass